So now we're going to consider the action potential, what it is, why it's necessary, and how it's generated. The whole idea of the action potential is to transmit a signal, that is the action potential itself, 1, over long distances, 2, with high fidelity so that the same action potential that appears near the cell body appears at the axon terminal a short time later, and 3, the signal has to be transmitted rapidly. So to illustrate these features, I want to turn to the stretch reflex, the knee-jerk reflex. And remember the point of the knee-jerk reflex. You tap the kneecap, it stretches the muscle. The stretch then generates an action potential in the sensory axon that goes all the way to the spinal cord. It then goes to a motor neuron, which goes back to the muscle, contracting the muscle, causing the leg to lift. Here's how it works. Let's watch. We're going to tap the kneecap, stretch the muscle, generate an action potential that's going to travel over the sensory axon to the spinal cord, then travel through a motor neuron to the muscle, activate the muscle, contracting the muscle, causing the leg to lift. Voila, that's the knee-jerk reflex. But notice what happened. First, the action potential that appeared at the muscle as a consequence of stretching the muscle appeared here in the spinal cord a moment later. It is exactly the same action potential, and that's what I mean by high fidelity. The second thing is the action potential had to travel about 2 feet along the axon, and that's what I mean by transmission over long distances. And 3, the action potential has to get there fast. If you want to move, you've got to have rapid signal transmission. Now let me illustrate the whole rationale of the action potential. And I want to illustrate it with an axon that has no action potentials, but rather only has purple potassium channels. And the problem is that a signal generated at one point on the axon by the electrode on the left will die out and never reach the end of the axon. And what I'm going to do here is show you Mr. Magoo, who's standing over here to the right, and his job is to detect a signal that's generated by the electrode on the left. And the signal is going to be the ejection of a bunch of positive charges, actually a finite number of positive charges from the electrode. And Mr. Magoo's task is going to be to detect those positive charges that have been ejected by the electrode. Well, what happens is the positive charges, of course, are attracted to the negative charges on the inside of the membrane, and most stay closest to the electrode because they follow the path of least resistance, but some of them migrate down to negative charges along the membrane and negate them. And what this does then is it creates a gradient of positivity. And I can view that as a change in membrane potential along the axon. So the point is that at the point where the electrode ejected all the positive charges, you would get a very large change in membrane potential. And if you get farther down, there's practically no change because you just ejected a finite number of positive charges, and they can just negate a finite number of negative charges. And Mr. Magoo's looking there. He says, I can't detect the change in membrane potential at all. Now things get worse because the change in membrane potential, that is the reduction in negativity, allows potassium to be forced out of the cell by its concentration gradient. So potassium is forced out all along the membrane where the membrane potential has been changed. And what that basically says is that all the positive charges that I've ejected into the cell have been lost by the efflux of potassium out of the potassium channels. So what's going to happen then is you're going to see no change in membrane potential after a while. And Mr. Magoo's going to stand there and he's going to say, has anything at all happened? I can't detect a change at all. And the reason that Mr. Magoo could not detect the change in membrane potential is because the signal generated at the electrode died out and never reached the end of the axon. So how can the axon generate a signal that does not die out along its length? It does it with special channels that are selectively permeable to sodium. These channels are different from those we discussed before because these channels have gates that are opened and closed by voltage. That is, they're opened and closed by the charges inside the cell. The channel has two gates that are opened and closed by voltage. One, an activation gate that's opened by depolarization and closed by repolarization. There it is, the activation gate. And here's how it works. The membrane depolarizes, it opens, and the membrane repolarizes and it closes. And two, it has an inactivation gate that is closed by depolarization and opened by repolarization, and is just slightly slower than the activation gate. Here's how they work together. There's the inactivation gate. Depolarize. The activation gate opens first, and a moment later, the inactivation gate closes. Repolarize the membrane, they reset. The action of the channel is self-limiting. It opens automatically with depolarization and then closes automatically, even though the membrane is still depolarized. It's sort of like a clicker. Click, 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 click. Watch. Opens, closes. The inactivation gate closes a jiffy later, but it always closes automatically, and the membrane potential is not changed. Repolarization resets both gates. Repolarization closes the activation gate and opens the inactivation gate, thereby allowing the channel to open to the next depolarization. The major point: whether the gates are open or closed is regulated by charge inside the cell. The activation gate is opened by depolarization and closed by repolarization. There is a very large driving force acting on sodium. It is driven into the cell by its concentration force and attracted into the cell interior by the negative resting potential. But the sodium ions can only pass through the channel for a very brief period when the activation gate opens and before the inactivation gate closes. And during that brief period, the membrane potential is driven to the sodium equilibrium potential, plus 55 millivolts. Watch. Depolarize, open activation gate, influx of sodium, gate closes, no more influx. Repolarization resets the channels. That's the way it works. Okay, so now we're going to see how these sodium channels actually work in an axon. So what we're going to do is put a whole bunch of them in an axon. And I'm only showing 3 here, but you sort of get the idea. And then what I'm going to do is I'm going to plot above each of the channels the change in membrane potential that occurs when the activation gate opens and when the inactivation gate closes. First for the first channel, then for the second channel, and then for the third channel. And then we're going to start the whole sequence of events with a depolarization in the lower left, right under the membrane, where it says depolarization starts here. And here we go. We're going to depolarize the cell. Watch the membrane potential. It's going to change. It's going to become positive. The positivity opens the activation gate. There's an influx of sodium. The membrane potential is driven to plus 55, and then immediately thereafter, the inactivation gate closes, and the membrane potential above just spikes. It goes way up towards the sodium equilibrium potential. That big spike in membrane potential is referred to as the upstroke of the action potential. But now you have a very positive charge under the channel that had just opened and closed, and that positive charge is then attracted to the negative charges downstream, and it's then going to open the second sodium channel. And you're going to get an influx of sodium. The membrane potential under it is going to go to the sodium equilibrium potential, and the membrane potential is going to spike. And then that positive charge will spread down to the next channel and open it, causing it to spike up. And then the inactivation gate closes, and the whole sequence repeats itself. Now you can see why the signal doesn't die out. It doesn't die out because it's reproduced at each point along the membrane by the sodium channels. So the action of these sodium channels are really a wonderful, actually an incredible invention of nature, and they work remarkably well. However, they only explain the upstroke of the action potential. In the next lecture, we're going to see how the sodium channels work in conjunction with potassium channels to repolarize the membrane and make the action potential a very, very short duration event.